Logistic regression is a type of statistical model used for binary classification problems. In simple words, it predicts the probability that an input belongs to one of two categories. For example, if we have two classes, one is student passing in the exam labeled as 1 and student failing in the exam labeled as 0, given the hours of study, logistic regression can predict if a student can pass in the exam or not. And logistic regression assumes a linear relationship between the independent variables and the log odds of the dependent variables. What do I mean by linear relationship? If we observe here, as the hours of study increases, the probability of student passing the exam also increases, suggesting a linear relationship between them. So when the relationship is linear, logistic regression can effectively model the relationship between the futures and the probability of a particular outcome. While logistic regression assumes linearity in the log odds space, it doesn't require the independent variables to have a linear relationship with the dependent variables themselves. It can be nonlinear also, as long as the combination of input futures linearly affects the log odds of the outcomes. Now what I'm going to concentrate in this video is why things are designed in certain way in logistic regression, how it makes its predictions, the entire math behind it, and how to build it from scratch. Let's start with how logistic regression makes its predictions. It uses logistic function, also known as the sigmoid function. The formula for sigmoid function is 1 divided by 1 plus e power minus z. So why this sigmoid function? Because the value of this sigmoid function ranges from 0 to 1. Let's say if some value of z is represented on x-axis and its sigmoid value is represented on y-axis, we will get an S-shaped curve as shown in this figure. Now if z value is too large, e power minus z value becomes 0 and the sigmoid value becomes 1. And if z value is too small, e power minus z value becomes infinity and its sigmoid value becomes 0. Thus this function maps any input to a value between 0 and 1, which can be interpreted as a probability, which is exactly what we need. For given futures, we need the probability of its outcome falling in one of the two classes. So what logistic regression does is it fits this S-curve to the data, allowing it to predict probabilities for each class. So how do we accurately fit this S-curve to our data? Let's say the input futures are represented as x. First we find the value of z, and the value of z is obtained by multiplying the input futures x with the weight and adding bias term to it. Then we will represent this z on x-axis and its sigmoid value on y-axis. Let's say the sigmoid function is represented as h of z. Then we will accurately fit this S-curve to our data by choosing correct values of w and p. The correct values of w and p can be obtained using gradient descent algorithm. Then we will choose a threshold value to make some predictions. Generally, a threshold value of 0.5 is chosen for logistic regression. If the sigmoid value is less than the threshold value, then it falls into class 0. If it is greater than the threshold value, then it falls in class 1. Let's say we want to predict a class for some input value x1. First we will substitute this x1 in this z value. Let's say the z value falls here and its sigmoid value is 0.3. Since it is less than the threshold value of 0.5, it falls into class 0. And if z value falls here and its sigmoid value is 0.8, since it is greater than the threshold value of 0.5, it falls into class 1. So this is how the classification is done in logistic regression. Let's understand how all this works in detail using some example. Now I'm going to take the breast cancer Wisconsin dataset from sklearn, which is used for binary classification problems to predict whether a tumor is malignant or benign based on various features. So I loaded the breast cancer dataset from sklearn's dataset and then I loaded it into the data and then I took the futures into X and its targets into Y. And then I created a data frame of this data. Let's see how this data frame looks like. So in this dataset there are 30 different futures and there are two classes which are malignant, which belongs to cancerous, and it is represented as 1 in this dataset, and the other class is benign, which are non-cancerous, and it is represented as 0 in this dataset. Let me also mention them here. These features are computed from a digitized image of a breast mass. These features describe characteristics of cell nuclei in the image. If for these features the target value is 0, it belongs to benign, and if target value is 1, it belongs to malignant. It seems like the first 5 rows in this dataset all belongs to benign. So let's see some random value in the middle. Let's say 50 to 60. Cool. So the 30 different features are mean radius, mean texture, mean perimeter, mean area, mean smoothness. Like this, the 30 features represents some characteristics of the cell nuclei. So for these values of the 30 different features, if the target value is 1, it belongs to malignant, means it is a cancerous cell. And if the target value is 0, it belongs to benign and it is non-cancerous cell. Now our job is to predict using these features what are the cancerous cells and what are all the non-cancerous cells. Now let's see if there is any relationship between these 30 input features and the target class. First I am going to bring all these 30 features into same scale by scaling them, and I am going to take their sum. So I have imported the standard scaler from the sklearn's pre-processing, and then I fit transformed the input features x into it. Now let's take their sum values. So sum is equal to So what I have done is I bought all these 30 input features into same scale like this, and then I took the sum value of all these. So what np dot sum of x comma x is equal to 1 does it? It takes the sum of all these value and puts them inside one value. So sum of all these is 45.42707, and then sum of all these values is 6.692 and so on like that. Now I am going to separate the sum values of the malignant and the benign. So what I have done here is I first created two empty lists named malignant and benign, and if the class value is 1, I pushed the negative value of the sum into the malignant. If the class value is 0, I pushed the negative value of the sum to the benign, and then I sorted them and I printed them. Now if you observe the both lists closely here, the values of benign ranges from -75 to +14, and there are more negative values in it than positive values. So all these values are negative up until here, and then there are some positive values in it, and the values belonging to malignant are ranging from -51 to 29, and there are more positive values in it than negative values. So it starts with a few negative values up until here, and all the remaining values are positive. So we can clearly tell that as the negative value of the sum increases, the probability of the tumor being malignant is more than the probability of it being benign. Now I have represented the data in a graph here. I have considered this green point as class 0 which are benign, and this rose point as malignant which belongs to class 1, and I have taken the sigmoid values in the y-axis which ranges from 0 to 1, and if we represent the negative value of the sum of the features on the x-axis, when the negative value of the sum is low, the chances of tumor being benign is more than it being malignant. But as the negative value of the sum keeps on increasing, the probability of the tumor being malignant increases compared to the probability of it being benign. Now this clearly shows the characteristics of a sigmoid curve, and if we are given the features of a tumor and we want to classify it as a malignant or benign, all we gotta do is calculate the negative value of the sum of the features and then calculate its sigmoid value. We will get a probability. If it is greater than 0.5, it belongs to malignant, and if it is less than 0.5, it belongs to benign. Now there is a problem here. This curve might not be the best fit curve for these data points, because we are simply representing the negative value of the sum of the features on the x-axis. In this case, we don't know how much a single feature is contributing towards an outcome. Like I explained before, the threshold value is chosen as 0.5 and the threshold point is situated at this point in this curve. If we move from left to right in the x-axis, at some point we will cross this threshold value. Now what is the optimal position of this threshold value? In other words, what is the best fit curve for this data point? It can be this curve with the threshold point here, or it can also be this curve with the threshold point here, or it can also be some curve like this with the threshold point being here. Now how do we find this best fit curve? To find this best fit curve, instead of representing the negative value of some of the features, we represent the value of z on the x-axis. Now how do we get the value of the z? Let's say the features are represented as f1, f2, f3 and so on, f30. First we will assign some weights to these features w1, w2, w3 and so on, and then we will multiply these features with their respective weights and then add them up like this, w1 f1 plus w2 f2 plus w3 f3 and so on, and then we will add Bayes term at the end. Now why do we do that? We multiply the weights to know the contribution of each feature to the prediction. For example, let's consider these two features. Let's say the feature 1 represents some radius value and feature 2 represents some smoothness value, and let's say the smoothness value doesn't contribute much towards the outcome, which means no matter what the value of the smoothness is, we cannot tell if it is a malignant or a benign. In that case, we multiply this feature with a small value of w so that its contribution is reduced. And let's say the radius value plays a big role towards predicting the outcome. For example, let's say the malignant has a large value of radius and the benign has small value of radius. In that case, we multiply this feature with a very high value of w so that its contribution is more towards the outcome. Like this, we do this to all the features, and Bayes term is added to provide some flexibility to better fit the data. So by taking the value of z on the x-axis, we will have a much better idea of how much a feature is contributing towards a outcome, and it ultimately helps us in finding the best fit curve for these data points. And to find the best fit curve, we need to find the perfect values of w for each of the features. So how do we find the best value? First we start with a random value. Generally everyone starts with 0, so we start with the weight values as 0 and Bayes value as 0, and then we iteratively update it using gradient descent algorithm, and then we find the best values of w and b. So what we do is, we first start with some initial value of w and b. We do some predictions and we calculate how far are we away from the prediction, and to know how far we are away from the prediction, we calculate the loss function, and the loss function used in logistic regression is this one, which is called binary cross entropy or log loss, which is minus 1 divided by n into summation of I equal to 1 to n yi into log of prediction of yi plus 1 minus yi into log of 1 minus prediction of yi. Here n represents the number of data points, the yi represents the actual outcome, and p of yi is our predicted outcome. Now let's see why this function is used as loss function and why this works perfectly well for logistic regression. Now this is the loss function considering the entire data. If we consider the loss value for a single data, it looks like this, which is L of I. It represents the loss value of the ith data, and it is equal to minus yi into log of h of xi plus 1 minus yi into log of 1 minus h of xi. Here h of xi is the sigmoid function, nothing but the prediction. Now if you don't know, the logarithm function looks like this. The log value will be 0 at 1, and if it is less than 1, it approaches minus infinity. Now let's say we are making some prediction and our true value is 0. If the true value is 0, this term becomes 0, and we will end up only with this term, which is minus log of 1 minus h of xi. Now let's say our model did some correct prediction, which is a number closer to 0. So this becomes close to log 1. Now log 1 value is 0, as we can see in this graph, and if we represent the sigmoid values on the x-axis and the loss values on the y-axis, and if the true prediction is 0, the graph looks something like this. As our model made correct prediction, a number closer to 0, our loss value also reduces to 0, which is in this case, here you can see that if the value is closer to 0, it becomes log 1, and log 1 value is 0. which tells that we are in the right direction. Our model made a correct prediction and the loss value is less. And let's say if our model made some incorrect prediction and predicted a value closer to 1. In this case, it becomes a log of 1 minus 1, which is nothing but minus log 0. Log 0 value is minus infinity, and minus into minus infinity becomes plus infinity. And our loss value will be a very large value, as you can see in this graph. As the h of x value tends to 1, the loss value tends to infinity, which it suggests that we are far away from the actual prediction since our model made the wrong prediction. And let's say if the true value is 1, in this case this term becomes 0 and we will end up only with this term, and this term is minus log of h of xi. And in this case, let's say our model made the correct prediction, let's say a value somewhere closer to 1. In this case, it becomes minus log of 1, and log 1 value is 0, and our loss value will be closer to 0, and it tells that we are on the right track. Our model made a correct prediction. As you can see in this graph, when the true value is 1 and h of x value tends to 1, the loss value is 0. And if our model made a wrong prediction and predicted a value somewhere close to 0, then it becomes minus log of 0, and we know that log of 0 is minus infinity, and minus into minus infinity plus becomes plus infinity, and our loss value will be a very large value, which tells that we are far away from the prediction because the loss value is very large, which is also represented in this graph. As the h of x value tends to 0, the loss value becomes infinity. So in this way, this function accurately tells how far we are away from the true value by calculating the loss. Now this is only for one data, and if we consider all the data, we need to take the loss value of all the data and take their average, which is nothing but this log loss function. Now we know that this loss function accurately tells how far we are away from the correct predictions. Now let's see how can we use this loss function to find the perfect values of w and b. Let's consider only one value of w and see how to find the correct value of w using gradient descent algorithm. So we start with some value of w, we do some predictions, and then we calculate the loss value for that predictions, and then we will update this w value in such a way that the loss value is reduced. And the way to do that is as follow: w equal to w minus alpha into dou L by dou W. Now here alpha is the hyperparameter called learning rate, and dou L by dou W is the partial derivative of the loss function with respect to the variable w. Now how does updating the w value using this formula helps in reducing the loss? If we represent the w value on x-axis and the loss value on y-axis, the graph looks like this. It will have the shape of a parabola, and to prove that the shape of the curve will be a parabola, I have written some code here. I have took some weights values and I have randomly selected some y true values and y prediction values as follow, and I have calculated the loss for each w, and then I plotted it in a graph. So as you can see, for different weight values, the shape of the curve is a parabola. Okay, now we know that the shape of the curve will be a parabola. Let's say the initial value of w is somewhere around here, and for this value of w, let's say the loss value is somewhere around here. Now we need to reduce this loss value. Now from this graph, it is clear that the loss value is minimum at this single point, which is called global minima. Now we are at this point in this curve and we need to move this point to the global minima. To do that, we need to move towards the right, which means we need to add some value to this w so that the loss reduces and this point reaches the global minima. Now let's say the w value is somewhere around here. Now in this case, we need to move towards left to reach the global minima. To do that, we need to subtract some value from this w. Now how do we know when to move towards the right and when to move towards the left? And to know that, we calculate the value of dou L by dou W. Now what this partial derivative of the loss function with respect to the variable w does is that it gives us the value of slope at a given point. For example, if we calculate the dou L by dou W value at this point, it will give the slope of the curve at this point. Now the slope here is a negative slope, which means that dou L by dou W value will be a negative value, and negative into negative becomes positive, so we will end up adding some value to the w so that the w value increases, loss reduces, and this point moves towards the global minimum. Now let's say we are at this point, and if we calculate the dou L by dou w value at this point, this time it will give us a positive slope. Since dou L by dou w value will be a positive, we will end up subtracting some value from the w so that the point moves towards the left and reaches the global minima. So now we know when to move towards the right and when to move towards the left. Now what is this learning rate doing here? This learning rate helps in optimizing the movement of this point to make it reach global minima. Let's say the learning rate value is not included in this equation. Then the equation becomes w equal to w minus dou L by dou W. Now in general, dou L by dou W value will be a very large value compared to the W. So if we start from here and we calculate the dou L by dou W value, we know that we need to move towards the right. It does move towards the right, reaches the global minima. Since dou L by dou W value will be large, it doesn't stop there. It overshoots and reaches somewhere around here. And if we calculate the dou L by dou W value here again, it will again be a large value, in fact even larger than the previous dou L by dou W value. Now here also we know that we will move towards the left. It again move towards the left, overshoots, and it reaches somewhere around here. Like this it will keep on oscillating, never reaching the global minimum point. And to control this, we multiply the dou L by dou W value with a learning rate. Generally a small learning rate of 0.001 or 0.001 are chosen. If we are here and we include the learning rate in the equation and calculate the dou L by dou W value, we know that we will move towards the right, and this time it won't overshoot up since we are multiplying it with a small value of learning rate, and this time it moved towards the global minima and the rest reaches somewhere around here. So the point moved from here to here. And then again we calculate the dou L by dou W value here, and again we multiply it with the learning rate. This time also it won't overshoot, and it again ends up somewhere much closer to the global minimum point, let's say around here. So the point will move from here to here, and like this after several iterations the point will eventually find its way to the global minima. So this is how the gradient descent algorithm works. It iteratively updates this parameter w by reducing the loss function. Now we know for sure that updating the value of w using this equation helps in reducing the loss, which ultimately helps us in finding the best fit position of the sigmoid curve to our data. Now we follow the same procedure for all the weight values and the bias values, and the way to update the bias term is also the same, which is b equal to b minus alpha into dou L by dou B. Dou L by dou B is nothing but the partial derivative of the loss function with respect to this parameter bias. So we know that updating the values of weights and bias using these formulas for sure reduces the loss function, which ultimately helps us in finding the best fit position for our sigmoid curve to the data. Now let's see how to calculate this dou L by dou W value and dou L by dou B value. Okay, now let's start with the loss function, which is L equal to minus 1 by n into summation of I equal to 1 to n yi into log of h of z plus 1 minus yi into log of 1 minus h of z. Here I consider the sigmoid function, which is our prediction, as h of z, which is equal to 1 by 1 plus e power minus z, and the z value here is w into x plus b. Now first let's partially derive it with respect to weight w. So I took the partial derivative inside the summation, and the equation looks like this: minus 1 by n into summation of I equal to 20 and partial derivative of yi into log of h of z plus partial derivative of 1 minus yi into log of 1 minus h of z. Now the derivative of the log x is 1 by x, so the partial derivative of this value becomes yi into 1 by h of z into partial derivative of h of z, and the partial derivative of this term becomes 1 minus yi into 1 by 1 minus h of z into partial derivative of 1 minus h of z. Now the derivative of the sigmoid function is sigmoid function into 1 minus sigmoid function, so the partial derivative of this value becomes h of z into 1 minus h of z, and by following the same rule the partial derivative of this function becomes minus h of z into 1 minus h of z, and we need to partially derive the z also, and partial derivative of this term is xi. Now this term and this term will get cancelled, and this term and this term will get cancelled, and then we end up with this one, which is yi into 1 minus h of z into xi plus 1 minus yi into minus h of z into xi, and if we multiply and rearrange them we will get yi into xi minus yi into xi into h of z minus xi into h of z plus yi into xi into h of z. Now this will become 0, and if we took the negative value inside it looks like this: xi into h of z minus xi into y of I, and if we take the xi common we will end up with this formula. This is the partial partial derivative of the loss function with respect to w, which is 1 by n into summation of I equal to 1 to n xi into h of z minus yi. Now the procedure for calculating the partial derivative of the loss function with respect to bias b is also the same, and at this point instead of calculating the partial derivative with respect to w, we do with respect to b, and the partial derivative of this term is 1. And so if we follow the same procedure and do the partial derivative with respect to b, we want to get this xi term, and we will reach this formula, which is dou L by dou b equal to 1 by n into summation of I equal to 1 to n h of z minus yi. Okay, now let's put it all together to create a logistic regression model. First we initialize the weight values and bias values as 0, and for number of iteration times we repeat the following process. First we calculate the value of z by multiplying the weights to the input futures x and adding bias term to it. Then we make some predictions for the current value of w and b, and to make prediction we just have to pass the z value to the sigmoid function, which is 1 by 1 plus e power minus z, and it gives us a probability value of 0 to 1. And using this prediction we calculate the value of dw and db. dw is nothing but the dou L by dou w value, and db is nothing but the dou L by dou b value. And then we update the value of w and b using this formula so that our loss value reduces. So in each iteration the value of w and b keeps on updating and the value of loss will keeps on decreasing, and after all the iterations are completed we will end up with perfect values of w and b. In other words, our sigmoid curve will have perfectly fitted to our data. Now how do we make the predictions? Let's say we are given some futures in x. To do predictions, first we calculate the value of z by multiplying it with the final weight and adding the bias term, and then we do the prediction by passing it to the sigmoid function. And if the prediction value is greater than 0.5, it belongs to class 1, else it belongs to class 0. Now let's see how to implement it in Python. Okay, we have already loaded our dataset and then pre-processed it. Let's just start with splitting this data into test set and training set. Now I have imported the train test split from model selection, which splits the data into training set and test set, and then I have splitted the data into training set and test set as follow. I have chosen test size as 0.2, means 80% of the data will goes into training set and remaining 20% will goes into test set. Let's see how training and test data looks like. So we have a total of 455 number of rows in the training data with 30 different features, and the remaining 114 data with 30 features in the test set. Okay, now let's start building the model. I am gonna name the model as a logistic regression. And let's start with the init function. So we're going to have self, and there is going to be two hyperparameters in it, which are learning rate. I'm going to give a default value of 0.001 to the learning rate and number of iteration, and I'm going to give a default value of 1000 for the number of iteration. Now let's initialize all this. Let's also declare the weight values and bias value here, and so for now let's give them value of none. Later we will initialize them with 0. Now let's implement the fit function. So def fit of, we need x train and y train to train the model. First we need to find how much data is in our training set and how many features are there in each data. So to know that we can use the xtrain.shape. If you can see here, xtrain.shape gives 455, 30. This 455 represents the number of data and this 30 represents the number of features, and I have stored them in n and futures. Now let's also initialize our weight value and bias value. So I'm going to say self.w equal to np.zeros of futures. So we are going to give each future value a weight. The number of weights has to be equal to the number of futures. So the np.0 creates futures number of zeros, and we have only one bias value, so I'm going to say self.b equal to 0. Now we know what to do. So for number of iterations, we calculate the z value, we predict passing it into sigmoid function, we calculate the dw value, dv value, and update the weight and bias values. So for I in range of self.number of iterations, First let's calculate the value of z, which is w into x plus b. So I am gonna say np dot of x train comma self dot w plus self dot b. Now this is the exact implementation of w into x plus b. If you don't know what np dot operation does, it works exactly like the matrix multiplication. So the x train dot shape, let's say the x train dot shape is n comma 30, and we have initialized the self dot w value with the future number of zeros. So it will have shape 30. And by broadcasting, if we are doing the dot product, Python will consider it as 30 comma 1. And if we are calculating the dot product of this and add the BS term to it, the resultant value will have a shape of n comma 1. As I said, it works exactly like the matrix multiplication. If we multiply a matrix of shape n by 30 with a matrix of size 30 by 1, we will end up with a matrix of size n by 1. And this is nothing but the exact formula, this one, w1 into f1 plus w2 into f2 plus w3 into f3 and so on, w30 into f30 plus b. Now let's get the prediction. I'm going to name it as a h. We just need to pass it into a sigmoid function. So I'm gonna say sigmoid of z, and I'm going to create a function that calculates the sigmoid value of z. So I'm going to say def sigmoid, z is the parameter, and I'm going to just return 1 divided by 1 plus e power minus z. Now let's calculate the dw value. We know the formula for the dw, which is 1 by n into summation of I equal to 1 to n xi into h of z minus yi. Let's implement that. Now I have taken the dot product of transpose of x train and h minus y train, which is exactly the implementation of this formula. Let's say the shape of x train is n comma 30, its transpose shape will be 30 comma n, and the shape of h and y train will be n. And if we apply dot product for this, we will end up with a shape of 30, which is exactly what we need. We just have to calculate the dou by dou w value for all the futures, and we have stored it in the dw. Now let's also calculate the value of db. Now the formula of db is 1 by n into summation of I equal to 1 to n h of z minus yi, which is a scalar value. So I'm just gonna say np dot sum of h minus y train. Now let's update the value of w and b. So self dot w equal to self dot w minus self dot learning rate into dw, and self dot b equal to self dot b minus self dot learning rate into db. Now that's it. This completes the training of the logistic regression model. Let's also print the loss value in each iteration to see if our loss is reducing or not. So I have implemented the formula for loss using numpy, and then I printed it here. Now this loss is exactly this formula. Now let's also print the final value of weights and biases to see how they look like. Now this completes our fit function. Let's also implement the predict function. So to predict, we just need value x. Now to do the prediction, first we calculate the value of z, which is w into x plus b, and pass it into the sigmoid function, and we'll get the probabilities value. And I'm gonna consider if the predicted value is greater than or equal to 0.5, it belongs to class 1, which is malignant, and if it is less than 0.5, it belongs to class 0, benign. Someone is supposed to say z equal to np dot x from self dot w plus self dot b, and I'm going to pass it into the sigmoid function. So I'm gonna say preds equal to 0 if p value is less than 0.5, else 1 for p in h. So what it does is it traverses through this h with variable p, and if p value is less than 0.5, it adds 0 to the list, else it adds 1 to the list, and I'm gonna just return the spreads. And now that's it. This creates our logistic regression model. Now let's create the object for this model. I am going to call it as a logreg and the logistic regression. So I am going to say logistic regression of let's go with the 0.001 as learning rate and 100 as the number of iterations. Now let's also fit our training data into it. So I'm going to say logreg.fit xtrain comma ytrain. Now if we see here, after the first iteration the value of loss is 0.693 and in second iteration it reduces to 0.691, and as the number of iteration increases the loss value is gradually decreased and it reached to 0.543 in 100th iteration, and this is how the W value looks like at the end. So this minus 0.029 represents the weight value of the first feature, and this minus 0.017 represents the weight value of the second feature, and so on, and this term represents the bias term. Now let's see how this model performs on the test dataset. Now I have passed the x-test values into the model's predict function and I have printed the prediction. So this is what the model predicted for the test data, and I have actually printed the predicted values and the actual values of the class side by side. So as we can see, the model is predicting the correct class for most of the data. Now let's see what is the accuracy of the model on test data. So I have calculated the accuracy by taking the sum of the times our model has predicted the correct class by the total number of predictions. So the accuracy is around 89.47%. So this is a pretty good accuracy. Let's say if we can improve the accuracy by increasing the number of iteration, let's say 1000 this time. So for the 1000 number of iteration, after first iteration the loss is 0.69, the loss value is gradually decreasing, and for the 1000th iteration the loss value is reduced from 0.69 to 0.247. So we can say that the model is trained well. Now let's see what its accuracy is, and the accuracy increased from 89 to 91.22%, which is a good accuracy. So the model is performing good, and that's it. This is everything about logistic regression, and feel free to correct me if I have explained anything wrong.